So last time we talked about the test format. I neglected to mention two things. So I'll give you the law of sines, law of cosines, and the area formulas for the test. And then you can make a half sheet of notes for the test. You put anything on it you want. It needs to be turned in. Ideally, it would have been today. I didn't mention it, so I'll still take things on Tuesday. So if you don't finish today, we should have like a half an hour at the end or so to do that. But if you want more time or whatever, you can come back and drop it off on me on Tuesday or send me an email with it in there and I can print it for you or whatever. Cool? But put whatever you want on there. It's up to you. Today, we're going to be starting supplement A, so it's like an extra chapter. In this supplement A, we're going to be talking about solving systems of equations. And in section 1, we're going to be talking about using graphing as our method to solve these things. Now, this is a recycled topic. You would have seen this in probably your Algebra 1 class and definitely in your Algebra 2 class. So at least the beginning pieces should be pretty familiar. But we'll start with a couple of definitions. So we want to start first by defining what we mean by a system of two linear equations. So when I say a system of two linear equations, I mean that I have two equations that relate to variables x and y that I can write in the form ax plus by equals c for equation 1, and for equation 2, dx plus ey equals f, where those a, b, c, d, e, and f are just constants, right? They're just numbers. Oftentimes, we would write a system with like one side of a curly bracket on it to represent that these two equations need to be taken simultaneously. But that's not like that doesn't have to be there, but that's usually, we often will see that. So let's talk about what it means to be a solution. So if these two equations are true simultaneously, a solution has to be an x and a y that'll satisfy both equations. So if I have an x and a y that satisfies equation 1, I have an x and a y that satisfy equation 2, the only place where they can be satisfied is where the lines intersect, right? That'd be the only point that satisfy, or only points where the two functions intersect can be solutions to our system. Everybody's okay with that? Okay. So let's do a quick example here. So we'll solve this by graphing. So I'll graph the first equation in red. I'll do the second one in green because it's Christmas time or something, or was recently. Ho, ho, ho. So how many points do I need to graph a line? 2. Could I do more than 2 if I wanted? Yeah. But why would I want more than the minimum, right? Okay. So what I can do is I can pick a value for either x or y, plug it in, and figure out what the other one is. So I guess I'll start by picking 0 for x. When I plug 0 in for x, what do I get for y? So 4 times 0 is? So I have y plus 0 equals 8, where it says y is 8. Everybody happy with that? And then maybe I'll pick 0 for y now. When I plug 0 for y in, what does x have to be? Two, right? Because if I plug 0 in for y, I have 4x equals 8. So x would have to be 2. Does everybody feel okay with that one? Okay, so we'll look at the green equation now. I'm going to do the same thing. I'll start by picking 0 for x. What do I get for y when I pick 0 for x? -6, because I have -3y equals 18. If I divide both sides by -3, I get -6. Great. Now I'll pick 0 for y. What do I get for x if y is 0? 9. Now, when I've done this problem, I've just picked 0 for x and then 0 for y. Do you have to do it that way? No. Any point is fine. I just did that because the arithmetic was going to be convenient, right? But there's nothing special about those values. You can pick any old values you want. It will be okay. All right, so now I'm going to plot some points here. All right, let's see. 2, 4, 6, 8, 10. Then we have -2, -4, oops, that's not right. -2, -4, and -6. All right, draw our stuff here in red. So I have 0, 8, and then 2, 0. That does not look very straight to me. Try that again. Ideally, I would use a ruler here, but gee willikers. Hopefully that's good enough. All right, 0, -6, and then 9, 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So my solution appears to be right about here. Notice that I'm not dead on, right? If I used a ruler, this would probably be right at a grid line. What point does this appear closest to? Maybe 3, -4. Is there a way that I can check that? Well, I can plug 3, -4 in for each of my two equations and see if that satisfies both equations. So it satisfies the first equation. satisfies the second equation. So I'm pretty positive that my answer is 3, -4. What do you guys think? Not too bad, right? The graph, or using graph paper, obviously is quite helpful there. But still doable. Or still need some neatness. And oh, I should have used a ruler. Look at this. I could have done this. How do I spin that now? There we go. There we go. See, there, I knew there was a way to do this. Isn't that awesome? OneNote's a wonderful thing, isn't it? Got some OneNote haters in the room. Okay. And look at that. Pretty dead on accurate there at -3 or 3, -4 there, right? It's a little better. I knew there was a way to do that. I forgot where that was at. Oops. Oops. There we go. All right. So maybe we should say so if I have a system of 2 linear equations, what sorts of outcomes can I have? Well, we've seen one already, right? We can get exactly one solution, like we just saw in the previous example. Right? What else can happen? The solution to a system corresponds to the graph of 2 lines. What else could happen? Do the lines have to intersect? Think back to geometry. Do lines have to intersect? No, man. What are those called? Parallel lines. That's right. So if you have parallel lines that never intersect, what do we say about that system? There's no solution. Right? Hopefully that's not super surprising. Now there's one other possibility. So lines can intersect once. They can never intersect. And what else could happen? They could be the same line. Very good. Yeah. So we call that coinciding. If they are the same line, how many times do they intersect? Infinitely many. Very good. Dead on. So if the 2 lines are not unique, if they're coinciding or they're overlapping, every point on the line is a point of intersection. There's infinitely many points on the line, so there'd be infinitely many solutions to that system. Now, if we say our system is written in slope-intercept form, where my first equation is y equals m1x plus b1, and y equals m2x plus b2 is my second equation. What can I say about the slope and y-intercepts if there's infinitely many solutions? What can I say about those two lines? Lucas, what did we say about these two lines? They're the same line. So what can we say about their slopes? And their y-intercepts? Also the same, right? Because they're the same line. The equation should be able to be written the exact same way, right? Okay. Okay, think about go back to geometry. What do you know about parallel lines with regard to their slope or y-intercept? The slopes are the same, but the y-intercepts have to be different, right? You know, if we look at these two, like clearly they had different y-intercepts, right? If they were the same, they'd have to be the same line. And what can we say about one solution situations? The slopes have to be different. So in a way, we should be able to look at our system before we even have to do any solving or graphing to kind of tell which type of solution we're going to get, right? One solution, no solution, or infinitely many. We doing okay so far? So when Mr. Kulik looks at this one, he immediately knows the outcome. Look at the coefficients between the two equations. You notice anything? What do you notice? Yeah, like 2 times equation 1 equals equation 2, right? That tells me there's going to be the infinitely many solution situation. That the two equations are really the same equation. Everybody go to that? Now, could we go ahead and write this into slope-intercept form and see that they actually give you the same equation? Sure. Is that a hassle? Yeah. I'd prefer to just make this observation and go on about my day, right? Much simpler. Okay. So what would a no solution situation look like? Say, let's take this example. What do you notice here? the x's and the y's are a factor of one another, but not the constants, right? So like the left-hand side of equation 2 is equal to 2 times the left-hand side of equation 1, but the right-hand side of equation 2 does not equal 2 times the right-hand side of equation 1. So this tells me there's no solution. If I wanted to, I could rewrite these things in slope-intercept form, and you'd notice that they had the same slopes but different y-intercepts, that they're parallel lines. Does everybody feel okay with like this little simple check we can do at the beginning for no solution, infinitely many solution? Save us a little bit of time on graphing if you make that observation.
If we do this, do we have to show a graph slope?
I guess it would depend on the directions of the question, right? If they asked to solve, no. They said solve by graphing, then yeah, but it wouldn't be so bad because at that point it's just like, I know I'm just graphing one and then it just needs to be parallel through the y-intercept so I can make the other one really easy. Kind of, you know what I mean? Like it does save us a little bit of time, but the directions kind of matter in terms of what it's asking for. You know what I mean? All right. The trickiest kind of thing we'll probably see in this first section is dealing with like some of these story problem scenarios. And this is good, probably review for ACT time because it's probably getting around that time for a lot of us. This feels very much like a classic ACT question. It says you ride an express bus from the center of town to your street. You have two payment options. Option A is to buy a monthly pass and pay $1 per ride. And option B is not to buy the monthly pass, but you have to pay $2.50 per ride. A monthly pass costs $30. After how many rides will the total cost of the two options be the same? All right. So in this situation, when I read this, I read two variables, two things that would be changing. So the number of rides in a month, I'll use a variable R to represent that. And then the cost, which I'll use C to represent that. Everybody's okay with that? So well then, let's define which one is our independent variable, which one's our dependent variable. Which one is the independent? Which one doesn't depend on the other? That's the dependent. Because if I ride 5 times, the cost changes. If I pay $15, it doesn't necessarily mean that right? Like it doesn't work that way, right? So the cost that I end up paying depends on how many rides I took. So I'll use R as my X coordinate and C as my Y coordinate. So I'll write my two equations for option 1. The cost is going to be the monthly pass plus the $1 cost times the number of rides I took. I think they were A and B. Option B, the cost is going to be $0 for the monthly pass, but $2.50 for each ride I take. And we're asking then, after how many rides will the total cost of the two options be the same? What we're looking for is the solution to this system. Everybody agree with that? Let's do this one on the calculator. Our calculator can do this, and this looks like a really obnoxious question to try to solve by hand, because I don't know how many rides might we take in a month. Maybe it's a huge number, like 50 or 60. It's going to be pretty annoying to graph this by hand. So I'm going to use the calculator to do this. So again, y is the same thing as c, and r is the same thing as x. So for the first equation, I just did 30 plus x. And the second equation, I did 2.5x. Is everybody okay there? Now I'm going to set my window. So x is representing the number of rides. Can that be a negative number? No, right? That doesn't make any sense in the context of the problem. So I'll set my x minimum, which represents the number of rides, as 0. What's the most number of rides that somebody might feasibly make in a month? I picked 60. That's just like you take one trip there and back a day. Like you went to your job, you rode the bus to get there, and then you went back home, you rode the bus to get there. 30 days in a month, 2 rides a day, one there, one back. I don't know, 60 felt like a decent upper bound on that. Feel okay to you guys? Does it really matter, that number? Not so much, as long as I can see the intersection when I do my graphing. I set the x scale to 10, so when I look at my graph, the x coordinates, or the x-axis is going to have tick marks every 10 units. That part doesn't really matter. The y represents the cost. The minimum cost, well, can't be negative, right? That'd be like the bus paying you to ride it. That's not how it works. So I put the minimum cost at 0. And then the upper bound for the cost, I don't know, I just put 200 in there. That felt like a heck of a lot of money to be spending riding the bus in 1 month, but. And then I did the scale for the cost by 50. Again, that just meaning I'm going to have like 4 tick marks on my y-axis. So then I hit graph. So this is the picture I get. What is it that I'm looking for from this picture? The intersection, this point right here. Everybody's okay with that? To find that point, my calculator can do this for me. So I'm going to press second and then the trace button here on the home row. Which of these commands are the one that I'm going to be interested in? Intersect, yep. Super obvious, right? So to do the intersect command, it's going to ask me 3 questions. It's going to ask me, which 2 curves do you want me to find the intersection of? And then make a guess as to where that intersection is. Now, how many curves did I graph? Just 2. How many times are those 2 curves going to intersect? Just once. If that's the setup, all I need to do is just press enter 3 times. And then my calculator says the intersection happens at 20, 50. So we can say if you ride the bus 20 times, the cost of the 2 plans are equal. Yes, sure. If you ride it less than 20 times, which cost or which option is better? If you go back and look at our graph, this line here is option B. Notice before they intersect, option B is lower than option A. That means it's the cheaper one. and after 20, option A is the better option. So you better be doing a lot of bus trips to bother with that bus pass is what it comes down to, right? It's a lot of time on the bus. What do you guys think on this? Pretty familiar? Should feel pretty easy, not a big deal. Section 2 is about graphing systems of linear inequalities. What's the difference between an equation and an inequality? An equation has an equal sign. Inequalities have, yeah, greater than, less than or equal to, something like that in there, right? So when we talk about a system of linear inequalities, it's basically the same thing as a system of linear equations, except you're not really limited to two inequalities. You can have as many as you want and still be a linear system in two variables. You can have lots of equations, or lots of inequalities, I should say. So let's just recap here how we graph an inequality, because it's been a little while since we've graphed one of these linear inequalities. So the first step is you need to convert your inequality so that it's written in slope-intercept form. Now, the one thing you have to be real careful about when you do that is if you have an inequality and you multiply both sides of that inequality or divide both sides of that inequality by a negative number, what happens? The inequality switches direction, correct? It changes from greater than to less than, or vice versa. Oops. Okay. The next step is you're going to draw your inequality just like you would draw the equation for a line, except if it's a less than or greater than inequality, we're going to draw our line dashed or dotted. And if it's in less than or equal to or greater than or equal to, then we're going to draw a solid line when we graph it. And then the last step is going to be that we need to shade on one side of our line or the other. To determine which side we should shade on, you can pick a point from either side, plug it in, and see if it satisfies the inequality. If it does, you shade in that direction. If it didn't, you shade in the opposite side. Or you can just use the inequality symbol itself would be enough also. All right, you ready to try graphing one of these systems? Sure. So let's do this one. So as an aside here, worth mentioning is that if we're solving a system of linear inequalities, The only way to solve this is by graphing. There's not any other method. Okay, this is a purely graphical situation. All right, so let's start with the first equation. I'm going to graph that in red. Because this is a just greater than, I know I have a dotted line. And it's because it's a greater than, we're going to shade above. So now I'm just going to pick some points. So I'll pick 0, and if I pick 0 for x, I get -5. And then I'll pick another value for x, say -4. -2 times -4 is 8. 8 minus 5 is 3. So for my next one, y is less than or equal to x plus 3. I know this is a solid line because it's an or equal to. And we're going to be shading below the line because it's a less than. So again, I'll pick a value for x. Pick 0, I get 3. Pick another value for x, I don't know, let's pick -3. When I plug that in, I get 0. I just picked the -3. Nope. So the arrow means that I picked that number, and then I plugged it in to get the y. So I just put the arrow next to whatever I'm picking, so that you guys can see if you're going back and working on stuff. It's like, oh yeah, he got that because he just picked it. All right, so I have 0, -5, 1, 2, 3, 4, -5. And I have -4, 1, 2, 3, -4, 1, 2, 3. Get my ruler out here. Okay, that looks pretty good. Oops. Okay, there's my dashed line. And it said we're shading above, so I'll draw like a little arrow up, reminding myself that I'm going to be shading above that line. Then I have 0, 3, so 1, 2, 3. And then -3, 0, 1, 2, -3. That looks pretty good there. This one is solid. And I'm going to be shading below. So where on my graph is going to be above the red line, but still below the blue line? It would be that stuff, right? That space right in there. Everybody okay with that? This picture is my answer. I can do a little check on this, though. It's not a perfect check, but it's something. What I can do is I can pick a point from that shaded region. Let's pick an easy point to deal with, like the origin 0, 0. If I plug 0, 0 into my first inequality, I get that 0 is greater than -5. Well, that's true. And then if I take my second inequality and I plug 0 in, I get 0 is less than or equal to 3. Well, that's true. So that point that I've chosen is part of the solution set for this system of inequalities because it satisfies both inequalities. So I'm pretty sure at this point that I've drawn my picture correctly. Is that perfect? No, but it's usually pretty good. All right, we'll do one more and then we'll be done for today. Sound good? Yeah, I love it. Get her done. All right. So here we're going to have 3 inequalities in our system. Again, it doesn't matter how many inequalities you have. You can have as many as it wants to give you. Just means the problem's going to be a little bit longer. But that's okay. Since it's a strictly less than, I'm going to have a dotted line. And because it's a less than, we're going to shade below. Find 2 points on that line. I'll pick a value for x. When I plug that in, I get -5 for y. Then I'll pick another value for x. I don't know, 4 is a good one. 2 times 4 is 8. 8 minus 5 is 3. Since this is an or equals to inequality, it's going to be a solid line. And because it's greater than, we're going to be shading above. We'll pick some points. I'll pick 0 for x. That gives me 8 for y. And then maybe we'll pick 4 for x. That gives -3 times 4 is -12. Plus 8 is -4. So my last inequality, y is less than or equal to -1/2 x plus 2. Because it's an or equals to, it's a solid line. And because it's less than, we're going to be shading below. I'll pick 0 for x. When I do that, I get 2. And then if I pick 4 for x, that feels like a good one, I get 0. All right, let's see. 0, -5. So 1, 2, 3, 4, 0, -5. And then 4, 3, 1, 2, 3, 4, 1, 2, 3. Put our ruler in here. That looks pretty good. Drawing dashed lines. Oops. That looks pretty good. So it's 0, 8. So 1, 2, 3, 4, 5, 6, 7, 8. And then 4, -4. 1, 2, 3, 4. 1, 2, 3, 4. Get our ruler back out. That looks probably okay. Okay. Put our ruler back away. 0, 2, 1, 2, and then 4, 0, 1, 2, 3, 4. And then get our ruler back out. Oops. Oops. Feels pretty good there. So again, this is a solid line. All right. The green we're shading below. The blue one we shaded above. And the red one we are shading below. So where's the space that's below the red line and the green line, but still above the blue line? That space there, right? Matt? Certainly. What do you guys think? It's not too bad, right? It's very much rehashing of like Algebra 1 and 2 skills that we should be pretty good with. If you're not, come talk to me. I'll help you work through whatever it is that you're having a problem with. And you guys should be able to do up through 8. Oops, that's not what I wanted to do.